All right, welcome back to class, everyone. Good morning. Hope you guys are all doing well. Let's have a look at our calendar here. So it is the 26th of September. We're almost to the end of chapter 3. We're almost done with it. We need to do a couple more hypothesis tests, a couple of sample size calculations, and then we'll be good to go. So that'll probably take about 30, 40 minutes to finish off some new material. Then we'll probably have about half an hour, 45 minutes or so to study and review for exam 2. So I've got a couple documents for that we can look over. So remember, exam 2 will open on Monday. It'll be open for these 3 days here. Do you have any questions about it? It'll be over chapter 3. I think there's about, if I remember correctly, about 13 to 15 problems. So it's designed to be about the same length as the first exam. So, there'll be, a couple of multiple choice problems. Most of them will be show your work style kind of problems, maybe a few true and false sort of problems. So no questions there. Well, let's go ahead and finish off our new material then, here at the end of chapter 3. Then you'll probably have some more questions after that, I think. Okay, so where were we? We were here on page 100. And yeah, so we were looking at the hypothesis test. So we've done hypothesis testing for the population proportion before. That was our first inference topic from chapter 2. Back in chapter 2, we did this by using the applet, which basically comes down to flipping coins. Here, instead of using the randomization applet, we use the normal distribution. Okay, and while we love the randomization applet, it's very useful. It's highly respected and commonly used in stats. The normal distribution is used more than the randomization techniques. Okay, so it's very important, even more important maybe than randomization. This idea of using the normal distribution. So we got about halfway through this problem, and then we ran out of time. So let me just kind of go back through this. Maybe we'll do a few calculations by hand. And then we'll do a couple. We have like 3 of these hypothesis tests in the notes, so I think we'll have lots of good practice here. So this was doing taste testing. So they're trying to see if people can tell the difference between diet soda and regular soda in a single sip. Okay, and so they randomly sampled 80 people, okay, and then they had 80 plain white cups. Half of them were filled with diet and half were filled with regular soda. And then using a random number generator, they assigned these 80 cups to the 80 different people. Okay, so basically, if you were one of these 80 people, you got a random assignment of either diet soda or regular soda. You take your sip, and then you decide if it's diet or regular. So out of those 80 people, 53 were able to correctly identify the soda. Okay, so do these data provide strong evidence that more than 50% of people, in other words, a majority, who claim that they can tell the difference actually can? Okay, so we state the hypotheses. Okay, and just like in chapter 2, there's 4 points to this part of the problem. Okay, you have to have H0HA, so that's 1 point. Then you have to have P and P, that's 2 points, your parameter. And so those 2 points right there, you can just sort of automatically just write them down, at least on this second exam. Exam 3, exam 4 will be different. Then the third point is getting the equality and inequality here. Okay, so the first one will always be equals. The second one will be some inequality. So it'll be a right-tailed, a left-tailed, or not equals. Two-tailed, right? So yeah, it'll either be greater than, less than, or not equal, right? And then so how do we know? Well, it says more than 50%. So that's implying that the alternative, the researcher's hypothesis is that P is more than 50%. Okay, and then the fourth point will be getting the number over here correct. Okay, so it says more than 50%, so it's pretty clear here that 50% is the correct number over there, right? So we state the hypotheses, nothing new. You did that in chapter 2, you've done it in chapter 3 now. So we calculate our p hat. So we're at 66%, got it right. Is that evidence in favor of the alternative? Well, yeah, it's not 50%. It is indeed more than 50%. But is it enough to be convincing? So it's about 16% higher than 50%. Who knows? Maybe that could just be due to random sampling error, right? And if we did this again, it would be much lower. It might be 51%, or it might even be 48% or something like that, right? So we're not, we're not convinced yet. We need our distribution. So we check the requirements, right? So the 3 requirements are here on the formula card. So if you're doing a 1 sample, which is what we're doing, right? We have 1 sample of 80 people. It's a z-test. We're using the z-distribution because p hat is normally distributed. Okay, and it's for a proportion. We're trying to figure out, what proportion of people can tell the difference in one sip. Okay, so, it's labeled here. So when you, go to the testing center, make sure you have the formula card with you. Okay, or you don't need the full formula card. A lot of this is not relevant, right? So make sure you take the relevant portions of the formula card with you. So we have to have a random sample, which we do have, right? They randomly assigned the drinks to the participants. We need to have independent observations. So that's summarized by this inequality here. So why do we need independent observations? Well, you don't want the people in the sample to be influencing each other or, related to each other in any way. You want them to be basically, not know each other. Okay, because people who know each other tend to influence each other. Okay, so the rule of thumb is as long as you have fewer than 5% of the population in your sample, then you should be fine. Then the third requirement is you need to have at least 10 successes and at least 10 failures. Okay, now this is a little bit different than for the confidence interval. For the confidence intervals, we use p hat. For the hypothesis test, we use p0. What does the 0 refer to? The null value of p. So it's basically using this value here. Why? Well, with the hypothesis test, the logic is we're assuming that the null is true. So assuming that the null is true, NP0 tells us about how many successes we would expect to get, right? So this NP0 here tells us about how many successes we can expect. And we need that to be at least 10, right? We need to have some people in both categories if we want to get a nice estimate for p hat. Okay, so we did this last time. I'm just recapping. We went 80 times 0.5. So if the null is true, we expect about 40 people to be able to tell the difference. And then we went n times 1 minus p0. So that also ended up as 40. And so we should be good. If the null is true, we should have enough in both categories. So with the confidence interval, you don't have to do the full formula. You can just say, well, there's 53 successes, but this is not a confidence interval. This is the hypothesis test. So we have to use p0 here instead of p hat. Okay. All right. So we check the conditions. We have all of those met. Then we want to think about our sampling distribution. Okay, so the sampling distribution is basically just like the null distribution we had for back in chapter 2 when we were using our applet. Okay, so in other words, p hat, if certain conditions are met, and they are met, we just check them right here, p hat should behave like a normal distribution. Okay, I mean that was a big part of what we did in chapter 3 is talked about the sampling distribution. Right? So if the null is true, then it's not a majority, it's just 50%. Then the null, the middle of that distribution should be 0.5, right? So the middle is 0.5 if the null is true. The standard error is given by this expression here. Okay, so remember, standard error for p hat is the standard deviation. It's the spread in p hat. It's how much p hat can be expected to bounce around. So we calculate that with our formula, square root 0.5 times 1 minus 0.5 divided by 80, and we get this 0.0559. So about 6% bouncing around there for p hat. So what we're going to do is we're going to find our p hat, then we're going to put that in this null distribution, and then we're going to see how much of the normal distribution, what proportion of it is beyond p hat. So it's very much like in chapter 2 when we put the boundary in and we counted those dots. It's the same exact idea, but now instead of dots, we have this normal distribution. Okay, so to get that value in the normal distribution, we're going to calculate our test statistic, and it's a z-score. Okay, so we have a p hat of 66%. What is the z-score for that p hat? Okay, in other words, how extreme is that p hat? Well, that's what the z-score tells us, right? The z-score tells us how many standard deviations away from the mean we are. So the formula for that is on your formula card. It's right here. And it really is just the old z-score formula, but with, in the context of hypothesis testing. So what do I mean? Well, it's still an observed value, right? It's still the measured value minus the mean, right? The mean is 50%, divided by the standard deviation. So it's still the same old z-score, just kind of the formula is a little bit updated to refer to hypothesis testing. And so we have all these pieces. We have p hat, it's about 0.66. We have p0 is 0.5, and then we have the standard deviation, standard error, right? So we actually calculated the standard error up here, so we can just put that in down there, right? So that's how far we got last time, just to recap. And so we found that, okay, p hat, yeah, it's possible that that's due to chance, and the null is still true. But if that's your position, then what you're saying is that you got a p hat with a z-score of almost 3, standard deviations away from the mean just by chance. And we know that that's unusual, right? Anytime you go beyond 2 standard deviations or so, you're getting an unusual result. Okay, so we're probably going to end up rejecting this. The next thing we need to do is the p-value. Okay, so the p-value comes from the normal distribution, right? We've verified that p hat is normally distributed. Okay, so in the z distribution, we have 0 there, and we have a z-score over here of 2.91. Pay attention to drawing this because you're going to have to draw this on the exam. Okay, so if you have a z-score of 2.91, what proportion of the distribution is above that? Well, that's a question we've answered many, many times in chapter 3, right? We open up GeoGebra and we go to the standard normal. Okay, so if it's a z-score, we know that it's been standardized, right? And so 0 and 1, then we want to find how many, what proportion of the distribution is above 2.91. So we go greater than, and we find that there's not much. Right? It's actually a very small percentage. It's about, that's not 2% there, that's 0.2%, right? So it's very, very unlikely that you would get a p hat of 66% or higher if the null is true. So what are we going to do? We're going to reject the null here, right? So 0.002 or 1/8 for the p-value. Okay. And then we can draw our conclusions. So we take, you guys know this step very well, right? We take the p-value, we take alpha. So the p-value here is 0.018. What is alpha for this? It says to use a 5% significance level. Okay, so 0.05. The p-value is less than alpha. since the p-value is less than alpha, we reject the null in favor of the alternative. So it does appear that among those people who say they can tell the difference in one sip, they're probably telling the truth, right? Or there's an element of truth to it because most of them can. Why do we reject? We reject because there is sufficient evidence to support the alternative. Okay, but remember at this last step, this is where we're putting the answer into context. We're putting our decision into context. So this is the formal decision, but it's not really something that most people, just the common person in the street is not really going to understand what that means, right? So the last step is where we put it into kind of plain language, right? So the plain language that anybody who wants to understand this can understand it. So how do we say it? Well, we say there's sufficient evidence to support the alternative or to conclude that the alternative is true. So what's the alternative? That a majority of people can tell the difference, right? So that a majority of people can tell the difference in one sip for that particular diet soda. So it doesn't sound like it's a super successful diet soda. So that was our first time through with the normal distribution. So I want to do a couple things here. First, let me compare this to our chapter 2 technique. Okay, so that chapter 2 applet with the randomization won't be on this second exam, but I still want to refer back to it to make a connection back to chapter 2. Okay, so this next part, we're going to just revisit our old randomization applet. We'll see that it gives us a very similar p-value. It's just instead of using the null distribution, the normal distribution, we're using a simulated null distribution. Okay, so let's do that. Unless there's questions, and if you need another minute to write this down, let me know. I don't want to go through this too quickly. I'll maybe give you another few seconds to write this down, and then we'll switch over to our applet for just a bit. Okay, so what applet am I talking about? This one here, right? So we put in the null value, then we put in the sample size. There were 80. Then we start drawing samples, right? So we get these, 80 flips of a coin, and we just keep repeating that over and over again, and we start building up that null distribution, right? So because it's software, we don't have to keep clicking the button every time. We can just do like maybe say 1,000 right off the bat, right? So what we're building up here is the null distribution, and you can see that it's quite normally distributed, right? Because the three conditions were checked, right? And so in chapter 2, what you did is you said, okay, well, there were 53 people who got it correct. What percentage of those random simulations did we get 53 or more out of the 80? Okay, and so it's very much like a normal distribution, right? If I draw the normal in there, then you can see, yeah, we're counting the dots, and it's basically the same as the area under the normal curve to the right of p hat. Does it make sense? So they're very similar ideas, and they're giving us very similar results, right? So let's do this a few more times. Now we're up to like 32,000 simulations, and if you look at that p-value there, it's 0.003, which is actually quite close to 0.002, right? So it's not the same, but it's telling us the same thing, that we should reject the null. Okay, so two different techniques. This applet here is the chapter 2 technique. Chapter 3 is the normal distribution technique. They're both useful, but only the normal distribution one will be on exam 2. Okay, so So I just want to make that connection back to our chapter 2. Now what I want to do is show you how to do all of this in GeoGebra very quickly. Okay, so I went through this at a snail's pace, going through all the steps, which is important. But we'd also like to be able to use software to do this more quickly. So let's look at GeoGebra. Okay, so go ahead and open up GeoGebra, and we'll do all of this in like 30 seconds using software. And we like that. I mean, we like to understand what's going on. We'd like to be able to do all the calculations by hand, so we prove to ourselves we know what we're doing. But it's also nice to be able to do things quickly. So to do this in GeoGebra, we'll go to the home page. And again, make sure you're using this URL that says classic in it. Okay, then we'll go to the toggle, the 3 dots, and it says probability calculator. You've been here probably 100 times by now. Then we go to the statistics panel, and we choose the correct inference procedure. By the end of the semester, you'll have seen almost all of these. At this point in the semester, you've seen one of them. Remember the z-estimate of a proportion, that's for a confidence interval. But we're not doing a confidence interval here, we're doing a hypothesis test. So it's not any of these, it's got to be one of these. So which one is it? Well, it's a test, and we're looking at the proportion, right? The population proportion P. So it's not a mean, so it's got to be one of these two. So it's either a difference of proportions or a single proportion. Well, there's no two proportions here, right? I mean, it's just a single sample from a single population. So the z-test of a population, of a proportion. Okay, so we put in the null value, which is 0.5, and we put in the alternative hypothesis. And the alternative is that we have something greater than 0.5. Now we put in the number of successes. There were 53 out of 80, and boom, it does everything for us. Look at that. We have our z-score of 2.91. We have our p-value of 0.0018. It's all very easy using the software. Okay, so make sure you can do that by hand. Make sure you understand all the formulas and that you can do that by hand. But after you do that once or twice by hand, go straight to GeoGebra and do these problems using GeoGebra. So let me do one more for you guys, and then I'll have you do one. No, I'll do 2 more for you, and then I'll have you do one. Oh, let's just go ahead and fill this in too, because this is useful. So explain what the p-value means. So we have a p-value here of 0.0018. Okay, so that's let's round that to a slightly easier number to work with. What is 0.002? That's not 2%. That's not 2 out of 100. That's 2 out of 1,000. Right? So what that one of the interpretations of the p-value is, okay, if you did this study many times, maybe 1,000 times, right? And it probably is repeated quite a bit, this sort of case testing. So let's say somebody did this experiment 1,000 times. If we did that 1,000 times, then a p-value of 0.002 would mean that in about 2 out of those 1,000 repetitions of the experiment, we would get something as extreme or more extreme than our p-hat if the null is true. So in other words, if the null is true and we did this, if we took 1,000 different samples, we would only get 2 about that are as extreme or more extreme than the one we got in our experiment. Okay, so we'd give sample proportions as high or higher, extreme or more extreme, than the one we obtained if the null hypothesis is true. Okay, so that means if people can't tell the difference between diet and regular. In a single sit. All right. So let me do 2 more of these for you, then I'll have you guys try one, okay? So on the next one, we're doing a political poll, or we're working with the results of a political poll, and they want to do a hypothesis test here. So, and it's actually from the text. So if you're reading the text, you read this example. There's a candidate for an office named Deborah Toohey, and her campaign manager claims that a majority of voters support his candidate. And that's kind of what a campaign manager is supposed to do, right? I mean, there's, typically they're supposed to be positive and, uh, you know, um, kind of bullish on the candidate, right? So, it makes sense that this person would claim that, it's more than 50% because, it means they're probably going to win, right? But the other campaign manager, right, the manager for the other one claims that it's less than 50%, right? Because, the other campaign manager wants, their candidate to win, right? So the other campaign manager is going to say, no, it's not more than 50%. In fact, it's less than 50%. So we have these kind of competing claims. So if we're not really sure what direction it goes in, remember the default is a two-tailed test, right? So just because one campaign manager thinks it's more than 50% doesn't mean we should assume that it's more than 50%. Sometimes results can surprise us. So a good default here would be the two-tailed test. So the skeptic's hypothesis is that the candidate does not have a majority of the votes, right? So we'll go with 50% for the null, and for the alternative, p is not equal to 0.5. So we have our hypotheses, and now we need our sample, right? If you don't have actual data, then you can't really go beyond writing out hypotheses, right? So we do have a sample. There were 500 likely voters, and 260 of them were in the success category, right? So success here is supporting Toohey. So what is that p hat? So p hat is 260 out of 500. So we're looking at about 52%. So it's a pretty tight race there, right? We don't have a super clear leader anyway. So 52% is not 50%. It is indeed not equal to 50%, but are the results convincing to you? Are they convincing enough so that you can reject the null in favor of the alternative? So, well, we need a distribution to do that, right? So let me do this kind of quickly so you can see the power of using the software, and then we'll go back and we'll be more careful with the details. So let me just assume that the conditions have been met for a second, okay? So for the null value, we'll put in 0.5. Then for the alternative hypothesis, we'll go to not equals. We put in the number of successes, sample size 500, and that's it. I mean, it's actually quite straightforward. So let's see. Make sure you are able to draw out the p-value calculation. So we'll have the normal distribution. It's the z distribution. Okay, so what we'll do is we'll get a z-score here and we'll find the p-value. Okay, so let's go over to GeoGebra and give this a try. Okay, I'll kind of reset everything up from scratch here. So we go toggle 3 dots, probability calculator, then put in the mean and the standard deviation. Sorry, what am I doing? We need the statistics panel. My apologies. Okay, so stats panel. Then we have to select the correct inference procedure. So it's a process of elimination. We know we're not doing a confidence interval here, so we're doing a test. Test for what? Well, it's a z-test of a proportion. Okay, so the null is that there's not a clear leader, right? So it's just 50-50. The alternative is that it's a two-tailed test. Okay, so we put in the number of successes. There were 260 in favor of TUI out of 500, and it's all done for us. Okay, so the z-score for that p-hat is 0.89, which means it's less than 1 standard deviation away from the null, which means it's not really unusual. So even if the null were true, that 52% would not really be that surprising. Okay, and we see the p-value there, it's a 37% p-value, right? So it's kind of a high p-value, right? So if we draw the results here, that means, okay, our z-score is about 0.89. And then the p-value in there is, what was it? It was about 37%. Yeah, 0.371. So what are we going to do? Well, we take the p-value, we compare it to alpha. So the p-value here is 0.371. Alpha is, it's not stated. So if it's not stated, then you have the liberty to choose your own alpha value. I always just go with 0.05. On the exam, it should be stated. If I somehow forget to state it, again, you can choose your own alpha value, but it'll pretty much certainly be stated for you on the exam. So since the p-value is more than alpha, we're going to fail to reject, right? So we fail to reject the null, and we say there's insufficient evidence to support the claim that there's a clear leader here in this election. So basically, neither campaign manager really should be saying that their candidate is winning, right? Because there's just not evidence of that. Okay, it's too close to call at this point. They'll have to wait until the election, right? So, any questions about that? I'll do one more, and then I'll have you guys do one. Okay, and this next one, we'll kind of go back through the details a little bit more carefully here. Any questions out there? Okay. So here we're okay. I do have a question. Let's see. I can't see that. Okay, so it seems like several people have been having problems with this. I don't know. Maybe they updated some of their software. Noah, are you using this website right here? If you click on that website, it should work. The thing about GeoGebra, they have lots of different products. They have lots of different, slightly different calculators, and it seems like several students this semester have been working with the wrong calculator. And if you're working with the wrong calculator, it will not have a stats panel on it. So you really want to make sure you're using the one that says classic here. The other thing sometimes, okay, good. Okay, yeah, yep. So yeah, the other thing sometimes GeoGebra is great, especially for a free product. It's great, but it never hurts to let me say, it does get a little bit glitchy sometimes after you've been using it for a while. So I just refresh it pretty frequently, and it works great, I think. Okay, let me do one more of these for you guys, and then I'll have you guys try one, and then we'll talk about sample sizes. Okay, so this is back to the idea of quality control, and we've done a couple of problems with about drive-through orders. Uh, Before, I think it was mostly about the time, but now we're looking at accuracy of the order. Okay, have you ever been to McDonald's or any sort of fast food restaurant? You get your meal, you drive off. It's like you 2 or 3 miles down the road, and you realize they missed the side order of fries or something, right? So it's kind of frustrating. And if it happens enough, you start to maybe go to a different restaurant, right? So, according to this industry magazine, Chick-fil-A has the highest accuracy of drive-through orders, and it's at 94%. So, in other words, 94% of the orders that are received through a drive-through at Chick-fil-A are accurate. So let's consider that sort of the industry standard, right? I mean, so, or the target. If Chick-fil-A's done it, then, all the other restaurants, are probably striving for that or even better. Okay. So we have a manager at a competing fast food restaurant, and she's done something with her drive-through, maybe reordered it. Uh, Maybe she's using different software, and for whatever reason, it seems to be more accurate than Chick-fil-A. Okay, so what is a hypothesis test that we could do here? And she even did a sample. Okay, so we have a random sample of 224 drive-through orders, 216 were correct. That'd be an interesting kind of sample to gather. How do you follow up on that and make sure the orders were correct? But anyway, that's a different step of the process. We're just thinking about the test here. So, what are the hypotheses? Well, what kind of data are we looking at? Each order is either going to be accurate or not. Okay, so it's a yes or no, which means categorical data, which means we're looking at P, the population proportion. Okay, so the idea is if there's millions of drive-through orders through well, at this restaurant, there's probably at least, hundreds or thousands of orders that are, going through the drive-through here. And we're trying to get an idea of what the accuracy rate is for all of those orders. Okay. But we don't have all of them. We just have a sample, right? So P is the proportion of all of the orders at this restaurant that are accurate. Okay. So we have H0, HA, we have P. We know that's going to be equals. And then how about the rest of it? Well, 94% is sort of, that target, right? So we know this is going to be 94%. That's going to be 94%. So we've got 3 out of the 4 points here. Then she's saying it's more accurate. So I'll have a greater than. Okay. So the skeptic's hypothesis is no, she's not, her system isn't better. The alternative is that yes, her system is better. Okay. And we like the skeptic's hypothesis there because, just because she says it's more accurate doesn't mean that we should all, everybody in that industry should invest in her, her system and change their system, right? You want to make sure it works before you adopt these new techniques. So what do we do? Well, we have a sample. So we look at the p hat. Okay, so the p hat here is 216 out of 224. Okay, so if we go 216 divided by 224, we're looking at about a 96% success rate in the sample. So that's the sample proportion success rate. So good for her. I mean, it does look like there's evidence that her system works, right? So this p hat here is 0.964. 0.964 is not 0.94. It is indeed more than 0.94. But is it enough, more than 94%, for us to conclude that this does work? Well, it's only 2.5% higher than 94%. So who knows, right? We just don't know until we have a distribution, okay? Or we could use our applet. Of course, we can use our applet, but that's chapter 2 stuff, and I don't want to go back to that too much. I want to work with the normal distribution. So before we can use the normal distribution, we have to check that the conditions have been met. Okay, so it says it's random. Okay, right, she has a random sample. So that's good. Then we have to make sure that the sample size is less than 5% of the population. So the sample size is 224. So 224 has to be less than 5% of the population. So what's the population? The population here is all of the drive-through orders at the restaurant that is being managed by this person, right? So, let's just assume she manages one restaurant. And so the population here would be all of the drive-through orders at the restaurant. So who knows what that is? It's not stated here. So we're going to do the next best thing, which is to solve for kind of a minimum population size. So we divide through by the 0.05, we get 4480. And so what that means is as long as this restaurant has, more than 4,480 drive-through orders, then that sample of 224 will be small enough, right? So that we have independence. Okay, and so we just, it's basically that's what we have to check, right? So that's all you can do on the exam unless I tell you, the population size. So if you do this, then you're good. Then we need to make sure the sample is large enough. Okay, so you have to have at least some successes and at least some failures, and the target is about 10. So we want to have at least 10 or so in each category. Let's see here.
Real quick, sorry.
It's fine. What's up?
I'm just curious why you're using why it says 0.05 and not 0.01.
That's yeah. So on this second one here, so it turns out that as long as the sample is less than 5% of the population, that the numbers, it'll basically act as if it's independent. So the people, the things, the objects that are being studied are basically just not influencing each other at all. We could use 0.01. I mean, 0.01 would be an even stronger statement, but here's the problem with that. I mean, if you have a very large sample, then if you're using the 0.01 standard, then you might actually have to throw out some of your sample. So I guess the answer is there's not really much of an advantage for us to use 0.01 because 0.05 works quite well. So does that make sense?
Yeah, gotcha.
0.01 would be more restrictive for us, right? So
But not
there's just no,
necessary for this.
yeah, it uh, the 5% rule of thumb, it functions just fine. I mean, I'd have to go through a little more math for you on another page to show it, but basically, the key here, the keyword is independence. You want the people in the sample to not be influencing each other, right? Because or knowing each other, influencing each other. You don't want all of your sample coming from one day, or like one family, right, or one town. You want it spread out across the whole population. So the rule of thumb is as long as it's less than 5% of the population, you're good. Okay, so I hope that answers your question. zero point zero 0.01 would
Yeah.
certainly also be independent. It would be even stronger than 0.05, but we don't need it. I mean, and it would be restrictive, because sometimes you do get a pretty large sample, and uh, we actually like a large sample just as long as it's less than 5% of the population. Okay, so then the third one here, we have to make sure we're expecting at least 10 successes and at least 10 failures. And let me point out that this is P0, it's not P hat. So it's not as easy as saying, okay, well, there's 216 successes. It's a little bit more complex than that. You have to go through the formula a little bit here. So we're going to go NP0. So N is 224. Be careful here. I do get a fair amount of students who write 216 instead of 224 there for whatever reason. So be careful with that. 0.94 is the null value here. So we're going to have 224 times 0.94. So we're expecting about 211 successes. So that's certainly more than 10. So if the null is true, then we would expect about 211 of the orders to be accurate. So that's number of successes if the null is true. So how many failures are we expecting? So again, we go 224, 1 minus the 0.94. So that's going to be, let's see here. So we go 224 times 1 minus 0.94. So 13.44. So if the null is true, we're expecting about 13 of the orders to be inaccurate out of the 224. And both of those numbers are more than 10, or at least 10, so we're solid there. So in other words, the normal distribution will work. So we can use it. So let's go over and use GeoGebra here to do that. So we go to the toggle, the three dots, probability calculator. We go over to the stats panel, and then the dropdown. So, just between you and me, on this next exam, there's only two of these that we've covered in this class, right? The z-test of a proportion, z-estimate of a proportion. So it's got to be one of those two. The others we haven't even talked about, right? So this is a hypothesis test, so of course it's got to be z-test of a proportion. So we put in the null value, 0.94, and then the alternative is that it's greater than. So we put in the number of successes, 216 out of 224, and we have it. We have a z-score of 1.53 with a p-value of 0.06. So 1.53, p-value 0.06. So let's write that down. So the z-score is your test statistic. So on the exam, I'm going to say, what is the test statistic? And you say, it's the z-score. And, just report what the z-score is. That's 1.5305. We'll go to 4 decimal places maybe. Then we have the p-value. And the p-value here is 0.0629. So you're probably also going to be asked to draw the normal distribution. Maybe not on every one, but at least once or twice. So we have the mean is 0.94. Okay, and then our test statistic came in at 0.96. 0.96 is higher than 0.94. And then the p-value is going to be the area to the right. Okay, so GeoGebra was nice enough to give us that value. So 0.0629 is our p-value. And so what do we do with that? Well, we compare the p-value to alpha. Oh, maybe I think I see where that 0.01 was coming from. Maybe earlier from your question. So 0.01. So alpha there is 0.01. The p-value here is more than alpha. So we didn't quite clear the bar, did we? Okay, so 6%, that's fairly low, but they're looking for a pretty low alpha. Why would they make the alpha so low here? Well, think about what a type 1 error would mean. A type 1 error, which is what alpha tells us, the probability of making a type 1 error, would mean that people start adopting this technique, right? And it's probably expensive, I would imagine. They'd probably have to buy some new machinery, maybe some new software, retrain their staff. And then what happens? They actually find out that it's no faster, right? So it's kind of wasted money, and they don't want to do that, right? So they are interested in new techniques, but they don't want to adopt a technique that doesn't actually help, right? So that's why they might have a lower alpha value there. And so since the p-value is greater than alpha, we fail to reject. Okay, there is simply insufficient evidence to conclude that the success rate at this restaurant is greater than 94%. We just can't prove that. Okay, it looks kind of promising, but this data set isn't adequate to prove it. So who knows, maybe she'll go back and get a larger sample later or something like that, but not yet. They're not going to adopt this yet. So I want you guys to try one of these hypothesis tests, and then we need to talk about sample size as well. So any questions here about this? I would like to remind you that I did post a review video that I made for some of my asynchronous online students. So you guys can use that for sure. It's pretty much like about an hour, and I go through a lot of, it's just sort of a typical review kind of thing. So we're not going to have a lot of time today. I thought we would get through this a little bit faster, but it has taken a while. So you'll want to look at that review video that I've posted there. And I also have that packet of review problems in that announcement. So let me just, before I forget, in case I do forget, let me just show you this exam 2 review recording. So you can watch that. And then even more importantly, you can go through these practice problems. So if you didn't use this on the first exam, let me remind you of this. Let me show you this. So what it is it's a list of all of the learning objectives for the whole course. So for example, in 1.2, we talk about defining terminology used in statistics. And then we have 2 problems for that. Okay, so it's a really nice way of studying for the exam. Okay, so chapter 1 isn't really relevant now. So you're going to want to go to the chapter 3 stuff. So it's a long document. It's kind of awkward for scrolling, but it's not that bad. So page 12, chapter 3 here, right? So go through those problems, do your best with that. And then after you finish those problems, I've got the key here. So go through the key and see how you feel about those problems. That'll help you out quite a bit. Okay, so we got the review video, we've got those review problems, and so yeah, I think that's pretty good. All right, so anyway, back to this problem here. We're looking at some sociology, a sociology study that was done. And if you're interested in sociology, social work, or social sciences, they do use hypothesis testing and confidence intervals quite a bit. Okay, to help them decide, if they're seeing something new or something has changed, something like that. So in 2000, let's say that there was a study done by the Census Bureau that was pretty conclusive, and they looked at the percentage of females 15 years and older, so kind of high school plus aged females, and 58% of them were living alone at that time. So now a sociologist believes that that percentage has decreased today. So for whatever reason, this sociologist thinks that something has changed and it's actually decreased. Well, just because you think it doesn't mean that other people are going to agree with you, right? In the social sciences, you're supposed to use data to prove certain, ideas and theories, right? So they have a sample here. So 500 females and 265 were living alone. Is there sufficient evidence at the alpha equals 0.05 level of significance to conclude the proportion has decreased since 2000? Okay, so I want you to go through this. I'll open up the breakout rooms if you want to join in over there. If you don't want to do that, then you can just feel free to work on it solo and just give it your best try. This is, very much like what you'll see on the midterm. Okay, so I'll just go quiet here for a little bit and let you guys work on it. Why don't we come back at about 12:32 together, okay? Okay, so can anybody tell us the final conclusion here? Do we reject or fail to reject the null? I'm just curious if anybody got it all the way to the end there on that. Are we going to reject or fail to reject here? Not so sure. So what are the hypotheses? So the skeptic's hypothesis is that the hypothesis of no change, right? So just because, it would be, just because somebody thinks it's changed doesn't mean we're going to believe it, right? So until it's been proven, we're going to just assume that nothing has changed, right? So it's the kind of the test of no change, sort of the status quo kind of boring hypothesis, right? The alternative is that it's decreased, right? So we're going to have less than 0.58. So we look at our sample, and we had 265 out of 500. So that p hat is, let's see, I forgot to write it down. So we have 265 divided by 500. So we're looking at about a 53% sample proportion. So in the sample, it is less than 0.58. So we do have, obviously we have some evidence against the null. It's not 58%. It does look like it's less than 58%. It's about 5% less than 58%. So is that conclusive? Is it statistically significant? So we have to check our requirements, unless you want to use the applet here. And that's one of the advantages of randomization. You don't have any conditions to check. But if you're going to use the normal, then you have to check the conditions, right? So let's see. It says random, right? So it says random. Okay, and then 500 is 500 less than 5% of high school age women plus for sure, right? But just for good measure, let's go ahead and solve this. So we go 500 divided by 0.05. So we have 10,000. Yeah, definitely there's more than 10,000 females who are at least 15 years old, right, in the country. So that's also the case. And then we have to make sure we have at least, or we're expecting at least 10 successes and at least 10 failures under the null hypothesis. So again, and I can't stress this enough, do not use p hat here. You have to use the null value for p. Okay, so we're going to go n 500 times the null value of 58%. Okay, so that gives us 290. So if the null is true, we're expecting about 290 of these females to be living alone. Then to see how many we would expect to not be living alone, we go 500 times 1 minus p0. Okay, so that works out to be about 210. 210 is more than 10. So we expect, if the null is true, we would expect about 210 of the females to not be living alone. So in both cases, it's more than 10. So we have enough in our sample here to do this. So we run over to GeoGebra, and so let's go from scratch here. We're going to go toggle 3 dots, probability calculator, and we go to the statistics, and we go to the dropdown. So this is a z-test of a proportion. So the null value is 0.58. The alternative is that it's less than, it's decreased. And we're going to put in our successes. We had let's see how many, 265 out of 500. And what do we get? We have a z-score of negative 2.27. So in other words, we're 2.27 standard errors below the null value if the null is true. So remember, we said that 2 standard deviations, plus or minus 2 standard deviations, puts us into sort of an unusual part of the distribution, right? So yeah, it's unusual that you would get more than 2 standard deviations away. and that's reflected in the p-value here of 0.01. Okay, so so we draw the normal. We put in the null value of 0.58. Our p hat is 0.53. The p-value for that from GeoGebra was 0.0117. Okay, so what are we going to do? We have our p-value, we have alpha. So the p-value here is 0.0117, alpha equals 0.05. Since the p-value is less than alpha, we are going to reject the null. We reject because there is sufficient evidence to conclude that the alternative is true. Okay, so what is the alternative here? The alternative is that the proportion of females who live alone has decreased. Okay, so we would say the proportion of females, and just, if you want to be really precise here, 15 years or older who live alone has decreased. Why? Well, that's why we call it the researcher's hypothesis. Why is it decreased? Because when you conclude this, then it sort of, opens up other questions, right? And that's what researchers like to do. They like to look at new ideas and try to figure out what's, what has changed, what's happened, why are we getting something different? That's what researchers enjoy doing. Okay, so that's several examples there of hypothesis testing. I think you'll be in, in a good spot there. The last thing we need to do is talk about the sample size calculation. Okay, so let's do that. And so the lecture notes, when we wrote the lecture notes, we sort of put the sample size calculation sort of sprinkled in through the section. But I kind of like doing it after we finish hypothesis testing. So we're going to go back a little bit. Let's see here. Okay, Killian's got a great question. How are you going to do that if you don't have software on the exam? So, well, it's kind of like on the first exam where we had that question about the randomization applet, right? And you didn't have the randomization applet, so how did you do it? Well, we had a screenshot in the exam, right? So you use the screenshot from the applet to answer the question. So the same thing will happen with the GeoGebra. We'll have screenshots from the GeoGebra. So I'm running a little bit low on time here, so I'm not going to have time to talk with you about this too much. But go through this document. It gives you example problems of what to expect on exam 2. So basically, you'll be filling in blank GeoGebra diagrams, and then you'll have some GeoGebra output that you'll be interpreting. So for example, on this problem here, you have the results from GeoGebra as a screenshot in the exam. Does that sort of make sense there, Killian? So you'll have enough of the partial, output from GeoGebra in the exam there to answer the questions. Okay, so if I had more time, I would talk more about that, but go through that document there. In the meantime, we need to do a couple of practice problems with sample size. Okay, so think about the whole process for doing research, right? At the very end, the final end of the process, you're going to publish your results, right? And so part of that would be probably doing a hypothesis test or a confidence interval. But those both require samples. So at the very beginning of the study, you actually need to create a sample. And then one of the major questions about the sample is how many people do you want to have in your sample? right? Do you just start calling people and then you just kind of stop when you feel like you have a big enough sample? No, it's more scientific than that. Okay, there's actually a formula for the sample size. Okay, and so it's here on your formula card. Okay, it's right here. It's called the sample size formula. And it basically comes from rearranging your margin of error. Okay, so basically if you take this and you solve it for n, you get the sample size formula. Okay, so it's not really that new of a formula, it's just the old formula rearranged. So what does it tell you? It tells you, all right, if you want to have a confidence interval at a certain level and you want to have a width for that confidence interval, then this is the minimum number of people you need in your sample. Why minimum? Well, because it costs money to talk to people. So we have our goal in mind, and what we'd like is to know the smallest number of people we can talk to that will still accomplish our desired confidence interval. Okay, so and then if you have more money and you want to talk to more people than your minimum sample size, then go for it. But we just need to kind of have like a floor in place telling us how many people the minimum is that we can talk to. So the formula is right here. You don't have to memorize these. But there is something else here to think about. There's actually two formulas. Okay, so there's this formula here, and then there's this formula here. Why? Well, when you're doing research, you're very often not the first person to do to study that topic, right? And so probably some of you are aware of how we do literature reviews. So if you're studying a particular topic, maybe you're a sociologist, you actually read the results of other people in your field, right? And then so often what I'm getting at is you'll have some prior information. So this first one here is when we have a prior estimate for P. Okay. The second version is when there's no prior estimate for your parameter. So the second version is when you're doing like your own like truly original research and nobody else has has done anything quite like it before. Okay, so if you have a prior estimate for P, then you use the first formula. If you have no prior estimate for P, you use the second formula. Okay, so let's pull those formulas over and use them. So let's say we have a school administrator. She's concerned about the amount of credit card debt that college students have. She wishes to conduct a poll to estimate the percentage of full-time students who have credit card debt of $2,000 or more. What sample size what sample size should be obtained if she wishes the estimate to be within 2.5 percentage points with 99% confidence? Okay, so there's two cases we're going to look at. Case one, where she has a pilot study. Case two, where there's no pilot study. What's a pilot study? A pilot study is sort of a quick, uh, maybe smaller kind of study that's done to give you an idea of what's going on before you do like a more formal research project. Okay, so so let's say that there's a pilot study out there that's already estimated P to be about 34%. So in other words, we have a prior estimate. So let's pull over that prior estimate formula. Okay, so we're going to go to the formula card and we're going to take this one over here. So we go n greater than or equal to z star squared. I'll just write it down here. So n greater than or equal to z star squared, p 1 minus p over margin of error squared. So you need three things. You need your critical z-score, you need p, and you need your margin of error. Okay, so p is the prior estimate. That's 34%. Okay, so we're going to put in 0.34 times 1 minus 0.34. Then in the denominator, we're going to put in the margin of error. So that is up to you as the researcher. Okay, you decide what kind of confidence interval you want, right? And you'll probably use the kind of confidence interval that's, commonly used in your industry or your field. So that's the margin of error, 2.5 percentage points. So we go 0.025. Then we need our critical z-score. So that comes down to how much confidence you want to have. If you want to have 99% confidence, then you have to go out a certain number of standard deviations. That's on your table here. Make sure you bring this table with you to the exam. Okay. So the critical z-score there is 2.58. So we're going to go 2.58 and square it. Okay, so it's calculator work at this point. Okay, so we'll go 2.58 squared times 0.34 times 1 minus 0.34. Okay, then we divide that by 0.025 squared, and we have our minimum sample size. Okay, we're going to have to talk to at least 2,389.9 people. Okay, but you can't talk to 9/10 of a human, right? So we're going to round that up to 2,390 people. So that's super useful, right? To know like how many people you need to talk to. Okay, that's if you have a prior estimate. But sometimes you don't have a prior estimate, right? So you don't have that pilot study, you don't have any other work that you can follow to give you an idea of what P is. So in the second case, we're going to imagine there's no pilot study, no prior estimate. So the formula changes a little bit. Okay, so this is the formula we're going to use. So it's going to be n greater than or equal to z star squared. And then instead of p times 1 minus p, we're going to put in 0.25. Why 0.25? Well, 0.25 is the largest value that p times 1 minus p can be. I can prove that if you know your algebra. I can show you that. And so what is it doing? It's basically planning for the worst. So it basically maxes out the needed sample size. So no matter what p is, we're going to have enough people here in our sample to create the needed confidence interval. Okay, so so here we go. It's the same z star. By the way, do we expect to have a larger sample size or a smaller sample size? If we don't have any prior estimate, does that make the sample size go up or down? What does your gut instinct tell you? Well, let's go ahead and calculate it as you're thinking about that. If we don't have as much information, right, that pilot study gave us information. If we take that information away, how are we going to make up for that lost information? We're going to have to make up for the lost information by talking to a couple hundred more people, right? So that sample size goes up to 2,662.56. Okay, so again, you can't talk to 5/10 of a person, so we're going to always round that number up. And now, because we don't have that prior pilot study, instead of talking to 2,390 people, we're going to have to talk to 2,663 people. So that's about 250, 60 more people. And, on a homework problem, that's not a big deal. But if you actually have to talk to 300 more people, that takes time, right? So we like prior estimates. That's one of the reasons that researchers look at the work that their colleagues are doing, right? So they can save some time and money, in this case. So we're all done. That's it. We kind of used up all of our time here. We didn't really get we didn't get any review in at all, but I mean, it's okay because I've got that review for you guys. It's a full hour anyway, so I think it's better. So also, I do believe that the STEM Center is doing some reviews So let's look that up. If you go over here to the the SLCC STEM Center, and you go to their tutoring, let's see here. I believe they have some class reviews. Yes, they have one on Monday that will be relevant for you guys. This one here on October 7th wouldn't really be relevant for you. It'll be after your exam, but this Monday one should be good. They should be going over the chapter 2 material. So if you can make it over there, that helps. But even if you can't make it to that, then you do have that review I put together for you in the announcement. So we're out of time. I'm gonna go ahead and excuse me, I'm gonna go ahead and sign off now, unless there's questions. Do you have anything you want to ask me about anything really? Okay, so yeah, there's the exam 2 review. All right, well, uh, we won't meet on Monday. I'll leave that that time available for you to take the exam if you'd like. So the next time we'll meet will be Wednesday next week. I guess that'll be in October, huh? Yeah, the 2nd of October. No, sorry. I don't know why I said Wednesday. We'll meet next Thursday, right, on the 3rd of October and get going with chapter 4. Okay, so have a good one, guys. Have a nice weekend and good luck on the exam.